I hope that doesn't cut off. Oh, you wanted it to make it bigger too, right? Oops. Oh yeah, I did. Curve midterm once. Do you guys get anything when I do something on the midterm?
Yeah.
Like probably you get a message or something. So this is what I did. I graded the midterm that you took home and submitted. But when I say graded, I did not give points for them. If you submitted, if I say satisfactory, that means I have given back 25% of what you lost. Okay, so that means if you got 60 out of 100, 40 is what you missed. So I gave 25%, that is 10 points. So if you got 60 out of 100, you get 10 points extra. Is that clear? Irrespective of what, if I marked you wrong in the submission. But in most of the papers I say redo. I request that you redo and submit. That means you did not do it satisfactorily. But for submission purposes, it is satisfactory. You won't lose your points. Is that clear? So, any questions on that? Okay, so here are your grades based on that's for midterm one itself. So this is, let's call it raw. That means whatever you scored in the classroom, right? So the scores were 87, 81, 80, 76, 62. So the distribution was pretty varied. It went all the way from a low to high, and then I gave back 25%. And I did not worry about the quiz here, but then all of you guys have 100% in quiz, so quiz really did not factor in my mind. So I gave back 25% of this, which made this, if you want, like if you do this exactly, let's do it 2 C digits, okay? So it's 90, 86, 85, 82, 72, 69, and 57. Okay, so that's so midterm that matters for your grade is this. So this is basically, you will see this in your D12, but if you check on it closely, it says 0%. So this is just for your information that this is what you got, but then after curve, this is what is used for all the calculation purposes and details. The total grade after all this, after you put in homework, everything, there I gave 10. So already I've given you 25% of what you lost, but this is only for midterm one. Now at this stage, I return back 10% of what you lost in the whole thing, like homework, quiz, anything that you have lost. So I give again. So that brings down your total. This is your total final at this stage. If I have to give you a grade, that is what I will use. So it is 93, 91, 91, 90, 81, 81, and 70. So it seems like I would say this is A, that's a B. Okay. That's that help? So again, if I were to give a grade today, but I get too lenient later on for various reasons, like take-home exams are a good way of doing that. But at this stage, that's what it is. So you need to, if you're satisfied, that's okay. If you're not satisfied, you should do whatever you can. Most of you guys know what you have to do. But if you want my suggestion on this, I can try to help. I won't promise I can. Okay. So, okay, so that's what. That's- I did post a homework, right? It doesn't show up here. So homework. Yeah, it is 5, yeah, when you reminded me, or I was working on it and you. Yes, so it was posted on Tuesday afternoon and the homework is due. Help me, so it is March 5th, I think.
Yes, March 5th. Next Tuesday.
Tuesday, yeah. And midterm 2 is April 4, anything else you guys want to point out? Oh, because. We started working on the example of pendulum. And broadly, we are saying this is Lagrangian mechanics. And using the methods we are going to be developing, you can do a lot of problems Lagrangian that are entirely you will see a lot of resources, a lot of textbook. It's full of examples. So I would encourage you guys to do a lot more examples that I'm going to be doing here. But I want to use the very simple example of a pendulum to clarify what exactly we do in Lagrangian mechanics or the mathematics of Lagrangian, what it is trying to do. So that's what I want to motivate here, even though it might seem like a simple idea of a pendulum. I'm redoing it here, but try to pay attention on why I'm doing it and what
Yeah.
what
A lot more steps involved in control.
correct. So often, for example, pendulum, if you're doing it at an introductory level, you can do this in 2 steps, right? So there is a restoring force that's it's like a harmonic oscillator. But let's do this in detail. So this is a pendulum example. We're doing a simple pendulum. It is probably also one of the first problem that was analyzed. Well, no, it may not be the first. Galileo was the one who realized that the time period of the pendulum is what is the time period of a pendulum? It depends on what?
Depends on G.
So it is
The length of the string.
Length of the
length and the acceleration due to gravity. It is very remarkable in the sense it does not depend on the mass of the ball, right? So no property of the ball comes in. It could be very light, very heavy. So it is very counterintuitive. So it is
Mass actually cancels out.
and mass actually cancels out. That is the reason why it comes out. But is that a true statement now that you have studied a lot ahead? Is that a true statement? Have you ever checked this?
Yeah. Yeah, I've seen videos as.
And you should do this in the experiment also, right? There is an experiment. Does that work?
I did go to the zoo once. They had the same kind of pendulum model set up showing simple harmonic motion of the.
So if I take a simple pendulum, like we even have grandfather clocks, right? Like, have you guys seen those clocks with a pendulum? Probably you guys are not. You've seen at least in your grandfather ancestral house or somewhere, or at least in movies, you've seen there is a pendulum which. But that requires a lot of mechanics. If I simply use a pendulum, will it show time period equal to constant? If not, why not? What's wrong in the? So if I were to have a simple mass hanging from a point, pivot, and I do the oscillations and I do the calculation, like I say that, okay, 20 oscillations or make it 100 oscillations so that it gets better, right? And then divide it by, measure the time and divide it by 100, will it match with L over G, square root of L over G times 2 pi?
It depends on the point you're taking oscillation. Right?
It
According to
depends
the
on the
experiment.
point. What's that?
The person who's taking the count is also there can be error.
Let's say you're very careful, extremely careful, let's say to 3 sig digits. Okay, I think in this case, let's say air resistance, you try to make it vacuum. How about that? Okay, make it. Yeah, yeah, ideal in the sense I'm trying to say that is this formula correct or not? That's my point.
It depends on thermal expansion.
Tell that again, yeah.
Expansions, thermal expansion.
What is thermal expansion?
Mhm.
No, not getting into the heat properties.
No heat. Yeah, let's say that can be avoided by regulating the temperature.
Temperature.
I think it will be correct.
Huh?
It is correct. I think.
It is correct. Okay, so then wait, it is wrong. It is not absolutely correct. There is a big approximation made in that.
Oh, the small angle.
Oh, small angle.
Small angle approximation, right? So unless you do that, like if you keep it within 3 degrees or something, if you want 2 or like 2 significant digits, you want to keep it within 10 degrees. Right? If you want 3 significant digits, you want to probably keep it in 1 degree. So how do all these clocks work? So there is a kick they give. So they design the clockwork in such a way that every time it loses the time, it gives a kick. So there is a mechanical system there that does that. So that's crucial. So the small angle approximation is very crucial. And then we want to see how does, so if it is an approximation, can it be solved exactly? It can be, and it is. And it's a special function. Usually in the introductory physics, we don't introduce it because mathematically we have not prepared ourselves for that. It is an elliptic integral, and we will try to. I should have done that as a problem in your homework. I usually do. Yeah, I miss that. Yeah, but yeah. How about that? So get the expression for no. Let's make this a little more serious quiz. There is a problem associated with pendulum in my earlier courses. It is usually in the first homework. Go about few years back. Usually it is the first homework I give. And try to, at least the last part where I try to say that what is the error, like how much will be the time period if you calculate it and how much will it deviate. Is that clear? It is in terms of elliptic integrals. So That was simply because I talked about simple pendulum. Here, I want to emphasize something about a constraint. So I want to introduce the idea of a constraint. So let's do a simple pendulum. We have a ceiling that is a point about which it is hanging, and there is a string that is mass m, which doesn't show up at all in the problem. It cancels out. That's angle theta, let's say, and it is measured. So this arrow means that it is positive in that limits. We recognize, let's go back to Newton's laws just to see what's the system like and what is the role of the two equations. Newton's law is a vector equation. Always, if it is in 2 dimensions or 3 dimensions, there are 3 equations associated with it. If it is 3 dimensional, it's 3 equations. If it's 2 dimensions, it's 2. And if it is 1 dimensional, there's only 1 equation. So this is happening in a plane. In general, even if you give a small amount of velocity in the other direction, it will be elliptic. So that's a different problem altogether. But we are saying that it is perfectly released so that it happens in a plane. So let's say this is a simple pendulum means that it is happening in a plane. That actually leads to the idea of what's a Foucault pendulum? Have you guys heard of a Foucault pendulum? Oh, I think it is Foucault.
That was
Spell check. Okay. Foucault is a French name, I think. What is a Foucault pendulum?
that, a two pendulum setup.
A true pendulum. Is that
Two.
two? No, that's a double pendulum. No, that's not Foucault pendulum. Foucault pendulum. Sometimes when there is an open house in our department, Bob makes this setup. Now the idea is that a normal simple pendulum, if you were to not make it move in a plane, if you let it allow in a rotations are allowed, that's a Foucault pendulum. Now what does it do? What will happen? Imagine the Foucault pendulum is on the North Pole. Okay, so you're standing on the North Pole and the Foucault pendulum is hanging from exactly at the North Pole. Earth is rotating, right? What will happen to the plane of motion of the pendulum?
Moving,
Will it move with the Earth? Like the whole room is rotating. Earth is fixed to the room is rotating. Will the plane of the pendulum, so let us say that's a reference, that corner is a reference. The pendulum was in the plane containing that corner and that corner, right? Now, as Earth is rotating, will it stay in that plane or will you see the Earth rotating around this plane? Is that clear?
yeah, you'll start to see it rotating, and Earth's rotation will affect the motion of the pendulum.
So that's not intuitive. That's not obvious. So you have to depend on the equations. Very good. But whatever Ryan is saying is that this plane will rotate. And how much time will it take to rotate? Right, 24 hours, right? It will come back in 24 hours. Now you do the same thing on the equator. Right? So now you do the same thing on the equator and you have, let us say the plane is in the plane of the equator. And you again ask what will happen. Now the rotation is in the plane.
Yeah, it's on.
So what would happen? Can you imagine that?
When it's hanging from the equator.
So you stand on the equator. So now the plane, so I think I can try to draw it here.
So we are looking at it from the
So
equator.
earlier, this was the hanging position, right? And now I'm saying that this is the hanging position. And here the plane of rotation could have been into the board, like everywhere the plane of rotation, the plane is into the board. Here also it is into the board. And now the earth is rotating about, so this is North Pole. That's equator. And this is rotating, earth is rotating. And the question is, what happens to the plane? It turns out it doesn't do anything. And the plane remains the same. So it is 24 hours here. How much is the time period here? It's not zero because it never comes back. It is infinity basically. So somewhere it's 24 is the minimum time period. And here it never comes back. So in principle, it's infinity. So what if you were to do this in Carbondale? Carbondale has an angle of what's the latitude of Carbondale? So it is, this is about, so with respect to the equator, it's about 39 degrees. For Carbondale, 38, 39 degrees, okay? But it's now in between. So now if you imagine this again, this will actually rotate. It will be larger than 24 hours, less than infinity, and you can calculate that time period. It will come out, I think, I don't know exactly how much it is in quiz. What is the time period of the plane of rotation of Foucault's pendulum in Carbondale? Okay. What's the time period of Foucault pendulums, plane of rotation in Carbondale? It is expected to be about 36 hours, between 30 to 40 hours. Okay, so that means to say that if Bob were to set it up and you wait for, and usually what you do is you keep this small bars here, it will come and hit on it. So it will start falling down. So after 36 hours, if you come back, it will make one full circle. But it is very easy to see about 5 degrees. If you stand in front of it for about half an hour, you will see that it will move around 5 degrees. So that's a Foucault pendulum where it happens not in a plane, it is moving in three dimensions. We are here going to do a simple pendulum. Everything is happening in a in a plane. What are the forces acting on it? I'm going to do this using Newtonian mechanics. So Newtonian mechanics, Newton. We'll come back and do this using Lagrangian mechanics, but I want to emphasize there's something in this. So this is mg. There is another force acting on it. That's the force of tension. And we agreed last time that there are only two forces acting on this. One is pulling it down straight towards the center of Earth. We are saying it's a uniform gravity. Again, you can imagine that this was not really uniform. It was a very long pendulum. At least hypothetically, you can say that the length of the pendulum is 5 times the radius of Earth, and there exists a point in space where it is actually being hung from. What will be the time period of such a pendulum? Please look. Okay. A very long pendulum, extremely long pendulum. So think of like the problem is you have Earth here now, radius r. And let's say Earth is static, it's not having rotation or anything, it doesn't really affect. And now I have a pendulum which is very long, make it 10 times the radius of Earth. Its length is 10 times the radius of Earth. And hypothetically speaking, there is a fixed point in there, and now I oscillate it. Okay. And what's its time period? Have you guys heard of this? What's the time period if I were to dig a tunnel in Earth from North Pole to South Pole? If I dig a tunnel and then I jump into it, what will happen to me? So you'll keep going down. Hypothetically, again, you cannot dig a tunnel that long, but hypothetically speaking, you will get faster and faster. And by the time you reach the center of Earth, you're going extremely fast. So you will overshoot the center and go all the way to the South Pole. And presuming there is no friction, you will reach the other place with exactly zero velocity if you started with zero. How much time does, then the question comes, how much time does this take? And any time heard of this? It's 42 minutes. One-way journey is 42 minutes, and 42 has some, what's the word? Jocular implication in the physics community. Have you guys heard of that? Ryan might have heard, because it's a,
Yeah,
no,
it comes up a lot when.
look up, Google, in a search engine, type, what is the relevance of 42? Okay, it's just a fun thing in physics community. It is considered as, what is it? It's the answer. So 42 is the answer to the ultimate question in the universe, something like that.
Yeah,
Okay, so it's a joke. It's not a serious thing at all, but here it comes out to be exactly that number, but it isn't having a unit. So anytime you associate some importance to a number, it should not have units. So it has nothing to do with that number at all. So it is 42 minutes, and it will turn out that this, so I said about the tunnel, right? It has inside of the earth coming in. If you take this pendulum and do the same thing, small oscillations, it will again be 42 minutes. So good problem to work on. It's usually, it can be in principle given in the introductory classes. Okay, all this, I'm starting with simple pendulum, all that is general information. We have two forces, so Newton's law tells us, Newton's law is for any mass, it could be big or small, and the acceleration of that mass, acceleration or the motion of that mass is given by the vector sum of the two forces acting on it. In this case, there are only two forces, vector sum of all the forces acting on the mass. In this case, there are only two forces. Let's, in principle, you can use any basis to analyze this. Let's use the basis, which is having a radial direction outward. So this is going to be our radial basis, r hat, and since theta is going in that direction, let's say, let me call this phi. Phi. Like it's kind of cylindrical coordinates, so I like to use phi for in angles in a plane. Okay. Now r hat and phi hat radially outward, tangentially increasing in the direction of the angle. The moment you choose your basis, then you take the dot product with those unit vectors and you get your equations of motion, right? So let's write that down. So let's do r hat. And what I will do is that I take the dot product in all directions, right? Basically, we're taking the component. When you take the component, you take the dot product. So mass times acceleration dotted with r hat is equal to mg dotted with r hat and plus t dotted with r hat. Okay. Acceleration in general, what are its components? What are the directions in which accelerations are? And here it is moving in a circle, so that we call, so this is a fixed length, right? So there's a length of the pendulum, let's say that's L. So what are the accelerations involved in circular motion? What's the direction of acceleration in circular motion? We talked about this last time also a bit.
radial and tangential.
Radial and tangential, there will be a radial component. Without that, you cannot go in a circle, and tangential if it is increasing. If this angular speed is changing, then that angular acceleration has to be there. So accelerations of information here. The acceleration A for circle, right? So radius fixed. If the radius is not fixed, there are more components. There is a Coriolis force and there is And there is a second derivative of position, right? That also shows up. So there are two more components that comes up. But if radius is fixed, I have minus r hat. So this is radially inward. This is the centripetal acceleration. And that's equal to omega square times r, where omega is basically d phi by dt. Right, rate of change of angle with respect to time. It doesn't have to be constant. In general, it changes, right? So this is derivative of angle with respect to time squared, and r is fixed, so that's L, right? So I can fix that, so that's L. Omega square L, and it is radially inward, and there is a tangential acceleration, and how much is that? What's the tangential acceleration equal to?
Equal to the radius times cosine of the angle.
No. So what's the acceleration in this direction, like radial direction? Introductory physics, R alpha, right? Alpha, where alpha is the omega by dt. That's second derivative of phi with respect to time, right? That's the acceleration, and you need a length, so it is alpha times L. Good. It is alpha times L. Nothing of this needs to be a constant. This is very generic statement. If radius is fixed, you have to, in general, you can have this acceleration. It is possible that it is going uniform circular motion. This is circular motion. Radius is equal to fixed is circular motion. What happens if it is uniform circular motion? Uniform is this, right? Steadily going in a circle. Non-uniform is going faster, slower, faster, slower. That's non-uniform, but you're going on a circle. So what happens in a uniform circular motion? In this equation, something changes.
That means the omega would be 0 because it's constant.
Or omega will be constant,
Omega will be constant.
will be constant.
No,
So,
Alpha is 0.
so alpha is 0, so this piece goes away. So if it is uniform circular motion, there is no tangential acceleration, right? Is this uniform circular motion when a pendulum is going? So pendulum falls on a circle, right? Is it uniform circular motion?
You neglect friction.
Start slow down.
So it starts with zero velocity actually at the very end, and it speeds up at the very bottom. And then slows down again, correct? So it is not uniform, so this is not zero. Right, it's not at all zero, so we need both. So put this component, so now I'm talking about r hat, A dotted with r hat is only this that survives. So it is minus M, right? M also. M omega squared L. This is the centripetal acceleration. This is the tangential acceleration, right? Let's take, so this is centripetal acceleration. You know this very well. I'm just reminding you guys, this is tangential. So that's the centripetal acceleration. What is mg dotted with r hat? So g is downward, r hat is this way, that angle between them is phi. So it is clear that it will be mg times cosine alpha. Right? And the force of tension is entirely along the direction of the tension itself. So it is minus T. Our hat is like tension is in the negative direction, so it's T. Okay. Question?
Was fine.
Cosine. Oh, okay, yeah. Perfect. Thank you. Cosine phi. Thank you. Okay, clear, thank you. Okay, again, we do this, probably have done this at some time or the other. Immediately by matching, oh, that's cosine alpha, that's a centripetal acceleration. I just wrote it as a vector and I'm taking a component, that is all I'm doing. This is the equation that we want to have, keep in mind, and let's stay there that way for a minute. Let's come back and do this for phi hat. Before that, any questions on that? Comments or questions?
So wait, for the equation of motion, you're only taking care of R hat.
I'm going to do the phi hat next.
Okay.
I'm taking the components. Usually we do this at a very geometric level in the in somewhere, most of the times when we do this at the geometric level. Here, I'm just doing it at taking the components, nothing deep in it. Okay,
Yeah, just organizing.
do the same thing again. Mass times acceleration, dotted with phi hat is equal to mg dotted with phi hat plus the force of tension dotted with phi hat. And again, you would say, in this case, this is alpha times L. So it is M times alpha times L. And mg dotted with phi hat is actually minus mg sine alpha. Not sine alpha, sine phi. And what is the component of the tension in the tangential direction? Right, it's zero, right? It is purely in along the radial direction, it is zero, so that's equal to zero. All right. So, if I rewrite this phi hat, notice m cancels out in the phi hat equation. Let me replace this. So this is your classic differential equation for a pendulum, and this is equal to minus g over L times sine of phi. And the second equation, let me write it as r hat is, let me write it as centripetal acceleration or P minus cosine phi, right? Now let me solve for the tension. Maybe that helps. T is equal to mg cosine phi plus the centripetal acceleration. Now, if you remember your pendulum problems, this is all we need for the pendulum. It doesn't care for this. It is coupled to this equation, of course. There is a phi here, it is coupled to this. But P is for all purposes a parameter. We don't fix this. This is just the nature decides that force of tension. Right. So this really doesn't come into role at all. Pendulum problem is decided by this equation. So this is dynamical. So this is equation of motion. The motion of the pendulum is decided by the angle, right? That's the equation of motion. So what is the role of this equation? Why this equation is there at all? Physically, what's the role of that equation?
What you can calculate the tension, which should
Yeah, if you want, you can calculate, but
over time, but that should also be constant because the ball still be acting on it, still falling on it.
sure, all that is correct. And here is a small interpretation I'm putting in. This is where I want to emphasize what Lagrangian mechanics is that this equation in principle doesn't have a role for dynamics. I could forget this, and that is what exactly you do in introductory physics. We write down this equation of component of this, that's the force, and that's sufficient. This, what it is doing is that it is trying to make sure that this is on a circle. The force of tension is just sufficient to match the centripetal acceleration. Because if it is going in a circle, there has to be a centripetal acceleration. The force of tension provides that force. But I don't care for that. If in principle, I'm not interested in the equation, in the force of tension. So this, just for emphasizing this interpretation, we won't call this equation of motion, just here, so equation of constraint. What's the constraint? That it has to go in a circle. Right? That's the equation of constraint that makes sure that the system is happening in a circle. Okay. So most of the time, so what Lagrangian does is that Lagrangian tries to get rid of this equation by using a coordinate. So if I started with the angle phi to begin with, then I won't even get this equation. So let's now do this problem again. Okay. And this time use the Lagrangian mechanics, and we won't even see this equation. There won't be force of tension at all to begin with when you do the Lagrangian problem. Later on, we will come back and try to interpret, no, where is the force of constraint? I want the force of tension. Then we will do what is called Lagrangian multiplier to capture this equation again. But the point I'm trying to make is that Lagrangian is good with problems where there are constraints, and it will get rid of that equation entirely by choosing a coordinate system. What is a coordinate system in this case? Angle phi. Phi is the only dynamical problem or dynamical parameter. So let's try to do that. So this was Newtonian mechanics. And by the way, I said this is the equation of a simple pendulum. Simple pendulum has sine of phi is equal to phi. That's a small angle approximation, which most of you said. So I had to go one more step, that this is a small angle approximation. So your quiz problem is equivalent to saying, can this problem be solved without small angle approximation? Okay, and the answer is yes, this differential equation can be solved, and the solution to that is an elliptic integral. Okay, so that was the quiz problem that I gave earlier. This equation can be solved, but not an easy function. You had to study elliptic integrals, but if you say there is a special function which is elliptic integral, solution comes out in those terms. Okay, so let's do the same thing again. A simple pendulum. This time using Lagrangian mechanics. And the idea of Lagrangian mechanics is this piece here. Look for constraints. Always there will be most of the classic Lagrangian problem will be a ball is rolling on a surface. For example, it could be a cone, it could be a sphere. In this case, a ball is not really rolling, it's hanging on a pendulum. So this length is fixed. Somewhere there is a constraint by geometry. So you exploit that. So let's do this problem again. This time I'm looking for the coordinates. So let's say this is the origin. That's my X, and that's my Y. That's my pendulum. In your homework problem, you will have two pendulums. Okay, so you have to look this, you have to complicate this further. So this is X and Y. In your homework, there will be an X1, Y1, and do this again. Okay, that will be your homework, so this will be x1, y1, and there is another pendulum, so that's x2, y2. Okay, and look for the constraint, this will be a length L1, this will be length L2, right? You have to look for constraints there. And but now I'm doing the simpler one, you guys do the harder problem. Okay, so x and y, that's your angle phi, and that is length L. What is the constraint? This pendulum has to go on a circle. Right, that's the constraint. How do I set that constraint? So look for the constraint always. The first thing in Lagrangian mechanics is look for a constraint. What is the constraint? L has to be fixed. L square is equal to x square plus y square. It's on a circle. X square plus y square. That's it. That's the main equation. And now accordingly, you have to look for some parameter if x and y is fixed. So one of them can be solved in terms of the other. But it turns out that the good parameter here is the angle phi that is increasing. So go for polar coordinates, and remember your Lagrangian is kinetic energy, which is V dotted with V, right? Minus the potential energy, which is due to gravity, it is plus, right? Minus of minus mg. And I have to decide on the vector. So notice, so vector r will be x and y, but that is somewhere here, right? So the moment I am in the fourth quadrant, so I have to be careful that one of them will be negative. When I say x, y, this is understood that it is in the first quadrant that they are positive. Here, automatically something becomes negative. So in that sense, g is downward or any g, so it is usually g dotted with r, right? That's your potential energy. So look for velocity. So velocity, so let's say x is equal to, write everything in terms of phi because L is fixed. So x will be L sine phi. Is that correct? X is L sine phi, so the opposite to the angle. And y will be equal to, this is minus L cosine phi. Good. I'm interested in the velocity, so velocity v is equal to I hat dx by dt plus j hat dy by dt. That's equal to, since you will see this in other places also, so let me make this general. What if this was not fixed? Okay, if L was not fixed, let me just for the moment, let's say R, and I'm going to replace R with L in a minute when R is not constant. So dx by dt would be equal to, there are two ways of changing it. So it's dr by dt cosine, no, sine phi plus r times sine phi is derivative is cosine phi, but now chain rule, so that's phi dot. So let me say this is r dot. Dot means derivative time here, so moment. So similarly, dy by dt is equal to minus r dot times cosine phi plus, no, no, but it's a derivative of cosine will make it plus, so this is r sine phi hat. I am interested in v dotted with v. So I have to, that's the same as taking a dot product here. So that's dx by dt square plus dy by dt square. That's equal to, I have to square this quantity, so that's r dotted square sine square phi plus r square cosine square phi dot square. And then the cross term plus 2 r dot phi dot r sine phi cosine phi. And I have to square this next, so plus r dot square cosine square phi square this plus r square sine square phi dotted square, and this is a negative sign, so it is minus 2 r dot phi dot r sine phi sine phi. These two terms cancel out nicely, and these add up. This is equal to r dotted square. It's sine square plus cosine square, and here again sine square plus cosine square. This is r square phi dot square. That's it. So the velocity square has this nice simple expression in a different coordinate system. Homework, or sorry, not homework, quiz, right? This is sort of in a polar coordinates, r sine phi, r cosine phi. These are polar coordinates, like except for this negative sign, familiar, like cylindrical coordinates. How will the velocity expression look like in spherical coordinates? Is that clear? So there will be three variables, r, theta, and phi. What will be the velocity square? Not just velocity squared. And that's a good expression to have in your mind for in general, like you should be aware that that is a simple expression. This is a simple expression, right? Velocity in the r and the velocity. And if you notice, this is again, maybe, what is the velocity? I wrote acceleration in the radial and tangential direction. What is the velocity in the radial and tangential direction? Generic. It is always true. What will it be? If it is going in a circle, that is phi half. Like if it is circular motion, uniform circular motion, what is its speed?
It's constant.
Constant. And how much is that in terms of, let's say, the parameters there? Angular speed, omega times radius, right? So omega r, right? Omega L, let's say. What is the radial component? It's r dot. That's the speed with which the radius increases. That's it. If you notice, if I were to square this, you get that. Right? Magnitude of this r dot square. Omega L square here is r. Is that clear? Right, this is an immediate consequence of that, but that's also perfectly fine. Is that clear what I'm emphasizing here? So rate velocity has these two, and this is a complete equation. This is not complete, by the way. Acceleration, this is not a complete equation. There are two more terms here. Here, this is for radius fixed. This is in general, right? If I fix the radius, this goes to 0. And this goes to 0, like L dot. So we have in our problem, we have only this as our equation. So my L or kinetic energy, so half m v dotted with v in our problem, the r is equal to L, that's equal to half m L square times phi dot square. The only difference again is that I'm using a constraint. I'm getting rid of everything that has a variation in that. So this equation will not show up. That's the primary thing that is going to happen. What is potential energy? So mg minus mg r. So it is minus mgy in that direction, right? So what is y is mg so I have to pick up, no, that's here 0, right? So it is minus and mgy, but y is positive, so it is plus mgl cosine phi. Is that correct? But minus mgl also, right? So what is y? So it's a median. So it is mgy, correct? And y is negative, so this is L. That's L. This will be L cosine phi. So y will be equal to, let's say, help me. Yeah, I think it is just mgl cosine phi. That's it. I was thinking I had to subtract this mgl, that is with reference to this point. So usually potential energy is with reference to a certain point. If I set this to be 0, then that is mgl minus that. So this is minus, right? So because I'm in the fourth quadrant. Good. Okay. And that's it, I suppose. So this is equal to, so now Lagrangian, which basically depends only on phi in this case. So this is equal to half m L square times phi dotted square. Minus of minus, that becomes plus m g L sine. No, what's the sign? I have an equation of motion in mind. I'm trying to do in my head and see if it gives the correct answer or not. I'm trying to foresee that. If that is a mistake or not. Okay, so that's your Lagrangian, and if you have a Lagrangian, your action is dependent only on phi here. It only depends on phi. That's your T1, T2, dt, and m L squared phi dot square plus mg cosine phi. Do the action functional derivative, we know that it gives the it gives the Euler-Lagrange equation, variation of action with respect to phi as a function of t prime here. This will be equal to t1, t2, dt. This is d phi by dt. So it is m L square phi. That's right. This is d phi by dt and d by dt of delta function t minus t prime. So I've done a lot of steps there. Hopefully, you guys have done sufficiently that you understand what I'm doing there. So this is minus mgl sine phi and delta of t minus t prime. So basically take the derivative with respect to phi dot, derivative with respect to phi, and set this to 0. This implies that this is minus d by dt of m L square times phi dot is equal to minus no, help me. So this is plus, right? Yeah. minus mgl sine phi is equal to 0. Again, you can directly use Euler-Lagrange equation. Euler-Lagrange equation is d by dt of dl by phi dot. That's equal to dl over d phi. Can directly use this as perfectly fine. The idea is that but now that you've had so much experience, you should be, if necessary, you should be able to do this. Like somewhere I can ask. So this will be in a sense more detailed, but nothing wrong in using this directly. So this will be d by dt of derivative with phi dot. You can directly do this here, right? So that's ml square phi dot. And that will be your canonical momentum, which is in this case the angular momentum. Right? That's one of the things in your homework. Sometimes you will see I ask you to interpret this, especially in a double pendulum. Like now there are two things. It will be something related to angular momentum, but you should be able to try to see through that. And this is dl by d phi. That's minus mgl sine phi. So this is mass cancels out, one of the L cancels out. So you have second derivative of phi dt square is equal to minus L over G times sine phi. Exactly the same equation, but this time this equation does not even appear. So this equation, because of our we foreseeing the fact that this is a constraint, we do not come across this. So in a sense, we have lost some information. We cannot calculate the force of tension in using this. But we will come back, and to a certain extent, we can fix that. We can try to capture the force of constraint. Also, that will be Lagrangian multipliers, and we will come to do that. Any questions on that or any comments? Again, I'm trying to emphasize the constraint. This solves everything in a way, right? The main important content was to recognize that this is a constraint and then to find a suitable coordinate. In this case, it is trivial. Trivial because we have done this so many times. If there is a entirely new problem you're dealing with, it may not be clear which parameter is which coordinate is the most suitable for the problem, right? So that's the challenging problem. Let's see in the last 10 minutes, I won't be able to finish this. In your homework, you do this for a double pendulum, right? So the best thing to do is, let me not do exactly the same problem, but I can now move this point, a constraint, right? How can I build in constraints? I can make this point move along a line, or for that matter, along a curve, right? That's also a constraint. So let me consider the following problem. So let's have point. Okay. Example. Let's have this to be our coordinates or the same problem. Earlier, what we had was the pendulum was hanging from this point, but now let's say the pivot point, wherever it was hanging from, that's free to move. So there is a small loop you can form here, right? Is that clear? So, and the pendulum is hanging off from here, and this is frictionless and completely entirely free to move. You could attach a mass there, M1 if you want, and M2 there, but make it massless, that's perfectly fine. Okay. If you have any discomfort in the fact that how can I introduce the mechanics of a massless problem, so introduce a mass M1 and set it to 0 later on, that's perfectly okay. But the main idea is that it is constrained to move here. So there is a point here, and this is again your x and y, that's your main point. So that's your phi. How are things changing now? My x now has a new variable in here, and this is, let's say, capital X. Same thing happens with a double pendulum. So yeah, let me say this is mass m1, right? Because double pendulum has this feature that they are on two circles. So here it is on a straight line. Double pendulum is on two circles. So that's the only difference. So how do I do this problem? This is x1, y1, and this is x2, y2. The constraints now is, so first one is the fact that y1 is always 0, right? It's along a straight line. That line is y1 equal to 0. Like first identify the curve on which it is. So the curve in this case is a very simple curve that y1 is equal to 0. I can make this go on a line, like on any line, for that matter, any curve, I can make it go on a parabola. Right? All those are Lagrangian problems which can be easily done. Just a small generalization of this, of whatever they're doing. And the second is the length is constant. L is constant, right? But what is that length that is constant? So let me do that better. So L squared now is, this is where the coupling comes in, x2 minus x1 squared. The position of the two masses comes in, plus y2 minus y1 squared, right? That's your two constraints. Okay. It's clear what are the dynamical variables. So this is the hardest part in if you're given a new problem. So these are called generalized coordinates. Generalized coordinates basically means which parameter or which variable describes motion. In this problem, m1 is described by x, right, or x1. So I don't have to write x because I have x1 here. Earlier I had x. So generalized coordinates are x1, y1 is 0. I don't have to worry about y1. And the second is the angle phi, right? And phi. Okay. Which means that this implies that my action will have two parameters, which will be x1 and phi. Like when I take the functional derivative, I'll be doing it with x1 and phi. So I have reached the stage where I get the Lagrangian, everything written in terms of x1 and phi. That's our goal. So use all the algebra to get rid of everything else. That's a strategy, right? I recognize which are the generalized coordinates or the dynamical variables which describes motion. Get rid of everything else. Okay, so very quickly, if I do this, so Lagrangian has kinetic energy, so it's half m1 velocity of 1 square plus half m2 velocity of 2 square and minus of the potential energy. Potential energy of m1 doesn't play any role. It is the same height all the time. And this is m2 g times y2, right? Yeah, and whenever I replace that y2 in terms of L, the negative sign will come in. Here, immediately you say that v1 square, so this is equal to half m1 x1 dot square. That comes out immediate. what is V2 square? So that requires a little work because V2 can depend on x1 also when it is moving. So let's do this a little carefully. So I have 3 minutes. So V2 is, so first to do x2. X2 is equal to x1 plus L sine phi. So x2 dot, which is needed for the velocity. So this is x1 dot plus L cosine phi dot. Y2 is equal to minus L cosine phi. Y2 dot is equal to L sine phi dot. Square this, x2 dot square plus y2 dot square, that's velocity 2 square, right? That's velocity 2 square I'm interested in. This is equal to x1 dot plus L cosine phi dot square plus L square sine square phi dot square. This is equal to x1 dot square plus 2 times x1 dot L phi dot times cosine phi. That's a square term, and the square term, there is a cosine square and phi square that combines to give L square phi dot square. Write that Lagrangian, so it is half times m2 x1 dot square. Notice from the second term there is an m1, m2 that is coming in, they combine m1 plus, it becomes m1 plus m2, and then you have plus m2 L x1 dot phi dot cosine phi plus half m2 L square phi dot square, and finally, so it is plus m2g, y2 is nothing but L cosine phi. That's your Lagrangian. Okay. Can I take 2 minutes more? Okay, so very quickly, let me do the L by the x1 dot, right? That's the first canonical momentum. That is m1 plus m2. X1 dot. Okay, there's only, oh, there's one more term here. Plus m2 L phi dot cosine phi. Right, that's wherever there is an x1 dot, you take the derivative of that. L by d phi dot is equal to m2 L x1 dot cosine phi. Arrange here, so this is plus m2 L square phi dot. And you also need the L by the x1, that should be 0, I suppose, it doesn't show up anywhere. So that's equal to 0, and the L by d5, there should be 2 places. So this is minus m2 L x1 dot phi dot sine phi, and this is minus m2g L sine phi. Equate this, time derivative of this is equal to time derivative of this. This is 0, which means that's a constant. Like something is 0 means that remains constant, and time derivative of this is equal to this. That's your second equations of motion. That's what you will do in your homework. Here I have put it on a straight line. In your homework, you put it on a circle. Okay, and I can take any curve, like in your exam, like I can put it on a parabola, ellipse, any simple curves, I can put it and you can generalize this very quickly. And at least until the stage of equations of motions, it's straightforward. That's what is best part of it. Equations of motions come immediately, but after that, is it solvable or not? That's challenging. And we will find a way whenever you do small angle approximation, we will see that it is solvable or it becomes solvable. Okay. Thank you. Made it, I hurried up at the last
In
one.
this case, will we use this equation to build a Lagrangian equation, or we use the action principle?
Now, at this stage, it is like the ab initio method, right? Once you know the method, the point is to get the equations. You can directly use it. But I can always come and ask you that, no, I want you to show that this is actually Euler-Lagrangian, this is the case. But most of the time, you can use it, but you should be aware of how it is done. So I recommend that at least once in a while, do the long way also, because you have done that so much. But if I don't ask you, you don't have to. Is this useful?